lot of additional costs here than a straight cylindrical geometry to this. So, but your AM, it reacts to the same whether you are going to make a cylindrical form of your design or this sort of complex design. In our case, so the manufacturing complexity is free. So that is the unique capability or the mantra of additive manufacturing. And then variety is free. What do you mean by that? Say you can make different geometries, different dimensions all together, but that can be done in a single go. That is the beauty of additive manufacturing. Your variety is free, so means you can produce in a single go different geometries, right? So that is absolutely not possible with the conventional manufacturing methods. We need to write a code for individual code for the individual component, but that may lead to, again, say more expensive. But here the variety is also free. You can make all these different geometries in a single go. So the variety is free and no assembly is needed. So you can make some 20 parts or 30 parts in a single component. Like it doesn't require any assembly at all. So means at least what we can do is you can do a lot of part consolidations in your product. So that will add value to your product rather than working with several components, right? So you have a unique advantage of that, and you have a zero lead time. Of course, the lead time. So you have a sort of logistics or supply chain involved here is very nominal supply chain rather than a huge supply chain in case of a conventional manufacturing systems. So you have a zero lead time here, which you can have another advantage, and you have unlimited design space. So this is quite interesting. So majority of the times in conventional manufacturing systems will curtail the designer's freedom, right? So designer may have in his mind, say about your product, so he inspired the nature or the biological designs. So the structure of the aircraft so may be inspired by adopting some lattice structure or by adapting some biological design, inspired design. But your manufacturing system may not be a hurdle for that kind of, say, design freedom that the designer is having, right? So you have an unlimited design space here in case of additive manufacturing. So you can very well print that component. So that is the another mantra or which you can come across in additive manufacturing. And zero skill manufacturing, what do you mean by this? So the conventional manufacturing systems, once you change the design, so even we need to train the people, or even it has to take several factors into consideration, and we need to train them. We need to have a lot of skilled people. But here it doesn't require much skill, but it's just you have the CAD data, a CAD model, and much worry about the other aspects which you come across in a conventional manufacturing process. But it's totally a zero skill manufacturing based system, and it's more compact, portable in size. Like we never thought that we are going to manufacture the components from our bedroom. So you have a desktop based printers. As of now it may be for polymer printing, but still in future you can expect, even maybe upcoming future, we can have all these printers, which we are going to have much democracy in printing or in manufacturing the goods right from the home. Need not go to any shop floor or need not go to a casting line. But that's a kind of a freedom, that's kind of a democracy that we are going to have in manufacturing through additive manufacturing process, and less wastage byproduct. So it is a zero wastage or a nominal wastage That is another mantra or the benefit, unique advantage of additive manufacturing. And of course, you have a infinite shades of material that is absolutely not possible with the conventional manufacturing methods. So you can have infinite material, multiple materials, or functionally graded materials, which you can have a certain material with one of the heads or one of the nozzles or one of the systems. Then you can use one material, other material, some electronic material, or some sort of polymer, or maybe you can have such a freedom even with the multiple materials or infinite shades of materials. It's quite possible with additive manufacturing technology. And even we can precisely say replicate the physical form once you have a sort of 3D digitizing system in integrating with 3D printing technology or additive manufacturing technology. You can play with soft to hard, hard to soft. So you can have such a compatibility with the digital data to the, say, physical forms, to the physical designs, or the vice versa. So with this mantra, or with these 10 principles of additive manufacturing, so why I'm talking this is your design for additive manufacturing should exploit these capabilities. So just don't simply use the additive manufacturing technology for the sake of, say, alternative, or say instead of machining process, instead of subtractive process, and instead of formative process, if you are using this process, absolutely you cannot get the benefits of this technology. So let us see, for example, you have some sort of a manifold like this. So this manifold, on seeing this, one can understand this design is not meant for additive manufacturing. Undoubtedly, this design is meant for machining. On seeing this block, on seeing this sort of a bulk design, so one can understand this is not meant for additive manufacturing. If at all, if you want to forcefully come and request saying that can it be manufactured through additive manufacturing. So now what I'm trying to say here is, say, for example, what are all the design approaches that you can come in additive manufacturing. So one way is direct part replacement, or without changing the design as it is, the intent of this designer may be keeping in mind that it is going to undergo a CNC technology. So, but your idea or your requirement, or you are forced to reproduce the design in additive manufacturing. So, for example, why you want to do that? Maybe some circumstances, some spare parts are not there with the manufacturer. So what, you never have an opportunity to change the design or the form or the fit or the functionality. So then that may be the one of the approaches. Then what AM is going to offer here. So if you are forced to fabricate through additive manufacturing this, then what sort of design for additive manufacturing approach, or your design thinking of an additive perspective? So then what should be done with this? What we can do with this sort of design is, you can use the process parameters at the optimum level. That's what you can do. Why? Because you are not allowed to change the design in the sense either form nor functionality or even fitment. So then if you are using simply instead of CNC to the AM, say for example, it may be consuming 4.6 kg of weight of this manifold, but you have another design approach, you want to adapt the additive manufacturing process. So then we need to change the form. Why we need to change the form? Why can't it be as it is? Why can't it be left as it is? Why? Because So you have a large masses here. If you have a large masses, you have a large residual stresses, and it will take a lot of time to build. Why? Because you have a large masses here. So you want to exploit the additive manufacturing. So you have the capability of minimizing the material, minimizing the weight of the component. So then you adapted additive manufacturing, say by changing the design, by changing this form into more convenient with the additive manufacturing. Why I'm saying that? So if you want to make this, so if you are using a laser based system, so the scanning of this, it will take hell lot of time. Why? Because it is not meant for the additive manufacturing, it is meant for the conventional manufacturing. So then that's what I have a freedom. What I have done is I have changed the form into a more convenient way for my additive manufacturing. But still, I didn't change the functionality. You remember that. I didn't change the functionality. I left the functionality as same, but I have changed the form. So without changing the functionality, I have changed the form or the geometry. So then I could be able to save a lot of material. 4.6 kg, now it has become 1 kg only. And you have 78% weight reduction through your additive manufacturing approach. Or still you want to improve the functionality. You want to improve the functionality. So for improving the functionality, I have redesigned totally. So I have redesigned the entire manifold. So in such a way that eventually I have reduced 1 kg to 0.4 kg, and even that is 91% saving in the weight. And not only that, so it has improved the functionality, that is the fluid flow, the performance of the system has been enhanced, and the fitment is enhanced. All three, that is form, fit, functionality, has been improved. So then you have a less space is required rather than this traditional design, right? So you have a lot of benefits once you can keep talking about, once you have adapted a DFAM that is designed for additive manufacturing into your practice, right? So this is a simple example, the importance of design for additive manufacturing. To, in a single word, you are redesigning the component and taking all the advantages or taking all the benefits, unique benefits of additive manufacturing. Then only you can say that is DFAM, design for additive manufacturing. So then come to this stage, but don't reproduce the things with the design, that the conventional design intent, but don't do that. You are not going to get the benefit out of this technology, right? So that is the underlying thing which we need to remember, right? So with this background, even we can extend the same discussion. So with the same manifold, say other manifold here. So where if you are using a solid block manifold, say for example, the scan time means if you are using a laser based system, so if you see the cross section in this is a block kind of a thing, so it will take hell lot of time to scan and to build this component, say 191 hours to scan this entire bulk or the huge block, a block kind of a design. But instead of a block design, you made it as a shell design without compromising the functionality. Say you remove the masses wherever it is not contributing any functionality, just you retain the functionality of the product, and you remove the masses. Why? Because it is a quite reverse approach. So CNC will remove the material, but it will add the material. While adding the material, let it be as less material as, but not like huge masses, huge bulk, right? But huge bulk may be attractive for CNC. Why? Because if you have more complex geometry and you have a huge wastage and huge exponential growth in the cost, right? It's quite contradicting scenario here with your CNC to the additive. But like once you have a shell based block, you perform the same say build time analysis or the scan time analysis the versus this solid block to shell block. So it is consuming only 36 hours for scan, but still you have a good DFAM guy. So you have a good design for additive manufacturing guy. So then further you could able to reduce to 19 hours, 36 to 19 hours by adapting some sort of best orientation possible or support structure optimization, things like that. So then when do you get this advantage? Until unless you have your design philosophy, that is as for your additive attitude or the additive capabilities, are you going to exploit that or not? Your design is not exploiting, then you don't call that as a design for additive manufacturing, right? So you got my point, what I'm trying to say you have a huge reduction in the build time. Build time means cost. So you may be quoting, so your machine cost may be say $65 per hour is the machine charge you are going to say quote unto the customer, right? Say the material weight is 7.4 to 1.23 to 0.5 kg, which you can know the importance. The material cost also reduced so drastically here, and your cost is also reduced drastically from 15K to approximately 2K US dollars save. So this much saving in terms of cost, in terms of time, or in terms of functionality. The other important thing is your DFAM will increase the functionality of the product. So you are going to get a double benefit. You are going to improve the performance of the existing system versus traditional design to the DFAM design, and of course the cost justification, the more economic or the economics involved in it, right? So with this, then we'll go to the real scenario of DFAM. I hope you got the scope of design for additive manufacturing, what should be done, right? So in a single sentence, you can say DFAM is nothing but you are redesigning the product in all aspects, maybe form, maybe function, maybe fitment, but with the intention of increasing the performance and of course reducing the cost also, right? So with this backdrop, then we'll see the process plan of typical additive manufacturing system. Say we need to start with the CAD design to STL file. So still the STL file is a de facto standard, but some of the machines even can take like 3FM or AMF file formats, which is of much informative than STL file. But STL file, but still it is going on as a de facto standard. So CAD to STL file, where your CAD model is a true geometry, that is a native format of your CAD design. But at the moment you convert as STL file, so you are compromising something. You are approximating the model with a triangular mesh, and which we need to even increase the resolution by increasing the number of triangles, or the here your accuracy will be improved once you increase the resolution of your, as we know that if you give garbage in, you will get the garbage out. If you are giving the input to the machine like this, less accurate model, but you may be impression that you have made this very accurately as a true geometry, but at the moment STL file, so you may lose this accuracy, the resolution, which we need to at the CAD or while converting to STL file, which we need to increase your resolution by increasing the number of triangles maybe. And then further next step is to slice them. So this for slicing, so you may be using a thicker layer, thinner layer, again depends on the range will depends on the type of technology and the material you are using it. So it depends, like say where you are slicing, which it should give and more accurate. But again, it's a trade-off between your accuracy and the build time, right? So then your DFAM will also address that. So, and even once you have generated the slice contours, and which we need to hatch it, or which we need to fill that contours by your laser paths if it is a laser driven machine, or it should be extruded if it is a nozzle based technology or extrusion based technology. So which we are going to you have a very good freedom here. You can get some other parts maybe as you wish, the sort of density or the sort of filling density you can vary. That depends on your application. Sometimes intentionally you are making a porous structures, or sometimes you are making 100% dense components, or you have you can have a control over here about your mechanical properties, about your say physical properties, which you can have a control here. So you can say change your tool paths as for your requirement. So even once you have done that, say cross sections has been generated, or your code, your G code, for example. So you are something like your G code in case of a CNC. Here also you have generated that code and it will be sent to the machine, right? And let us talk about the part orientation. So the orientation that you are going to build the component, so that will lead to the degree of anisotropy. So the additively manufactured parts are suffering from anisotropy. So you cannot expect, or you cannot get the same property, same mechanical property. One sample has made with one orientation, other sample has made with other orientation. Not only mechanical property, the accuracy is also varying from one orientation to other orientation. So then you have to understand and you have to fix which orientation is the optimum orientation, right? So where you can minimize your staircase effect, or where you can minimize the errors while fabricating it. You cannot eliminate, but you can minimize. Why? Because by nature you are adding the material from layer upon other layer. By physics of the system, like the phenomena that you are going to adopt here is you are going to experience some sort of inaccuracy, some sort of staircasing effect. Say, then how do you minimize that? If at all, if you minimize, of course you can minimize. So then how do you get minimize that? So why? Because everything leads to cost of your part. Why? Because say your design for additive manufacturing will talk about all these aspects. Means how best you can improve the accuracy at the same time in more economical way. So then one can work on all these boxes, right? So of course the thickness of the layer thickness, the resolution of your part is also dictates your layer thickness. The layer thickness, if you go with the more thicker layer, you can quickly finish the component. Means the build time is quick. The lesser time you can do, the cost will be less. But again, you have a trade-off between your accuracy and the build time, which we need to focus on that, which we need to come out with a sort of optimal way of making use of these process parameters, setting of these process parameters. And of course, your support structure. So your support structure, once you vary the orientation, so you will have different quantity of the support which it needed, and not only the quantity of the support that it is getting consumed in each and every orientation, but how do you get remove, or how do you get remove this support material? The post processing cost is also much involved. And sometimes if you are giving support structure internal geometry, internal features, and it is very hard to remove that, and unnecessarily you may increase the production cost, right? And even a good design for additive manufacturing guy will work on, say, instead of using this much quantity of the support, simply a less amount of supports, or by redesigning some of the features in the product. So with the compatibility or with ease of additive manufacturing, say, then we are redesigning this. So then with this scope, I hope you got some idea what is a design for additive manufacturing is all about, and what should be done, and various say parameters that we need to consider, the rules or thumb rules, some of the thumb rules, some of the constraints of the machines and the technologies capabilities, which we need to, say, use all that, right? So then we'll be focusing on the part orientation. So your part orientation is the parameter. So that is going to affect in all aspects. Means what? The outcome of your part, each and every outcome of your part, maybe quality, maybe mechanical property, maybe physical property, microstructural property, metallurgical property, whatnot. Like say, all that is getting affected by your part orientation. So by selecting a right part orientation, so that is the job of a good designer for additive manufacturing. So your part orientation, so maybe you may come across a different criterions. Maybe a part height criteria means the Z height is minimum, so the number of layers or less. Means what? So you can make a part if you vary the orientation. In one orientation, say it may be 100 mm height, but if you vary the orientation to some other orientation, it is only 50 mm height in that orientation, particular orientation. Means your setup time is less. So means your 50 layers has quickly finished, rather than it is double the setup time for 100 layers, right? And that the time, build time, is nothing but your cost. So you have it, as we know that this technology is expensive, but how do you bridge that thing here by adding some value to the product, and by manipulating these parameters, or by exploiting these capabilities of AM, and as well as the constraints or the rules, the, the rules that we need to adopt, right? Say you have one of the criterions, or the height criteria, or another criteria, the quality. Why? Because you may get better quality in one orientation than other orientation. So you have the quality is totally dependent on your the build orientation, and the area of the base that your part is resting, means you have much foundation. So you are looking at, means again it depends the type of material you are using, it that is also varying your these selections, or this sort of analysis, or this sort of thought process, right? So it's all about thought process, right? Say um, then how do you do this? How do you make use of these at the optimal level, right? And sometimes your mechanical property is the criteria. So you are much affected by the anisotropy of this anisotropy nature of additively manufactured parts. So your mechanical properties are quite different from one orientation to other orientation. The use of external support structure, again it is adding cost. The support material cost is as equivalent to model material. If at all, if it is allowing to introduce two materials, but some of the technologies may be restricted with only a single material, like powder bed system, right? So which you don't have any thing to add, then in that case you may using the same material as also support material, the same model and support material. It's costing you, it's more expensive. All the way you may have 5,000 rupees per kg to 25,000 rupees per kg, like titanium material, right? Maybe steel, maybe aluminum, maybe 5,000, 6,000 per kg, all the way to 25 kg with the titanium, right? You don't have a luxury to say have using this expensive materials, right? Say, then how do you say minimize those costs? How do you use optimal utilization of this stuff, right? Say, um, then that's about all design for additive manufacturing, right? Say, how do you select these kind of things? Say, part orientation, as we discussed, the 5 criterions in the previous slide. Say, you can have 5 possible orientations. Maybe one orientation may give a maximum area to the base, better foundation, or minimum area of contact with the support for less damage of your say model material. And then another important thing is, which we need to understand, the functionality of each and every feature that are there in your product, and then accordingly we need to say vary the orientation also. Why? Because you are suffering from anisotropy, right? So then how do you make use of how do you compensate that weakness, right? So that's the thing where we need to. And minimum height of the object, maybe one orientation, the number of layers or less, or minimum facet roughness, or minimum volume of the support. So you can prepare some sort of artificial intelligence or some sort of decision making system where you can even come out with, though you have the software which it is connected with the AM machine, so it may suggest some sort of orientation. Of course that may be the Z criteria, the minimum height criteria, but not all the times that will work out, but which we need to see the functionality of the component. So here the design for additive manufacturing, or in general AM, states that function first, material next, but it is quite reverse for the conventional manufacturing practice, right? Say, yeah. So then we can have a totally different mindset or different approach. Your conventional thinking or the conventional manufacturing mindset, it's quite no. It won't work unnecessarily. It may add the product cost, right? But which we need to think additively, right? And which we need to redesign accordingly. So I'm talking about like which you want to exploit the AIM technology. Yeah, the conditions applied. Otherwise, simply I don't want to do that. So as it is, I want to process. Okay, you absolutely you can do it, but whether you are getting the advantage of all unique capabilities of AM or not, that we need to. And of course, your build orientation is also, as I said, like surface finish. For example, you have theta is the angle that you have, say, you have oriented. So theta is, say, for example, 45 degree, and you have another sample with 30 degree, and with the x is the layer thickness. With the same layer thickness, you are trying to compare the surface roughness of one sample with 45 degree build orientation, other is with 30 degree. So obviously the sample which it has been built with 30 degree, you have more exposed area, you have more error, you have more deviation than a 45 degree oriented sample, like where no, my intention is like how it is getting influenced your surface finish and even mechanical properties. So you have one sample that is made with 0 degree orientation, and you have another sample made with 90 degree orientation, and see the fracture mechanics of 0-degree fabricated orientation and 90-degree fabrication sample. So totally different fracture mechanics which you can encounter. Means altogether you have different mechanical properties once you vary the orientation, right? So one can understand this importance of this sort of selection of your orientation. Um, and these are some of the things, but even you have to, this is a thought process, like how you can say optimize these sort of things at the maximum level. And then we are talking about everything in terms of the economics, the cost of the production. So if you could able to say analyze the cost of your additively manufactured parts. So of course the total cost is pre-processing cost. What is the pre-processing cost? Say all your design for additive manufacturing. So which before you fabricate, before you generate the codes. So sometimes just now we are talking about we need to redesign it, or you may hire some design engineer, or you may hire some application engineer, or you may hire or bought some sort of packages to do this job, or you may hire manpower. So then your pre-processing cost is all about that sort. And your build cost, so the machine utilization cost, the machine hour running cost. So you have purchased the machine maybe 1 crore rupee, or 1 crore, even you cannot get a 1 crore metal AM machine. It may be all the way around 1.5 or 2 crores. So 2 crores maybe the machine investment purchase cost, and maybe you may add some interest to that, maybe 5% typically. So and then you by payback period, maybe 2 years or maybe 3 years the payback period, and running time. um, why? Because not all the 100% time you are going to print. Like you have a setup time, you have other purging time, you have a preheating time. Then you have a percentage of running time and yearly hour. That depends the usage of your machine, and you may be fixing the machine hour cost, and then you can get your build cost and your material cost plus, let's say, um, just I said like 5,000 to 25,000 rupees from steel to titanium per kg. Like say which your material cost is also like, as I already given, saying that one approach some 10 kg, other approach 5 kg, other approach 0.5 kg. A good design for additive manufacturing is consuming only 0.5 kg rather than a 7 kg or a 6 kg of material that you are going to say use it for various designs, right? So your material cost is also going to play a vital role, and it's the thing which we need to much cautious about it. And then post processing cost, the post processing cost, which we need to remove the support structures, we need to clean the surfaces, sometimes we need to subjecting to a furnace treatment, or sometimes we need to machine, sometimes we need to short pin it, or sometimes we need to bleed blast it, or that cost is also added here. So typically it may 30 to 40% cost may go, and your post processing cost is also reduced once you have a good design for additive manufacturing philosophy with you. And your post processing itself, you can redesign and you can do a better results for this, right? So my intention is like you try to know the importance of design for additive manufacturing in the recent times, especially for the metal printing. It's quite expensive than a polymer printing. It's like which we need to focus on that. So then next thing is a support structure, right? Say where the support structure is going to play a vital role. So then how do you get generated? How do you get optimized this structure, this support structure? Again, it's a different ball game once you work with different material, right? So it will behave differently, and say which we need to focus much on this support structure as part of your design for additive manufacturing. say process is concerned. So your support material, if it is a polymer based system, you don't have much difficulty or much concern about the support structure. So, but you may have these support structures which are needed for majority of the AM technologies. I hope around 80 to 85% AM processes requires supports. So even so, either it is a powder bed system, or whether it is a VAT based system, or or a material jetting, or a binder jetting, or a DED system, or whatever it is, like say, which we need to have some sort of general thumb rules, which you have the angle with the vertical particular feature with the vertical thing, some 45 degree. The overhang angle may dictate your whether it needs some support or not, right? So of course you do have a certain open source softwares to do this job for assessing your support structure and minimizing the support structure accordingly. um, then you have a simplify 3D or Cura, and this is meant for only the DIY kind of a printers, like say you have some extrusion based system like FDM or FFF kind of a thing. But if you are working for metals, definitely we need to have certain proprietary softwares that it should be adopted for this sort of supports that it should be. But what is this support structure is all about? So the support structure, so broadly you can classify the support structures into three different support structures. So you have a platform or a substrate. Say on top of it, you will be starting with a certain number of layers with a support without damaging your directly. If you are printing your model right from the first layer, so then how do you get detached? And while detaching, you may damage your surface, right? In that case, which you may use some kind of a separator kind of a supports initially on top of this say platform. And you have a main support. So the main support is one which it never contact with the model, right? So you have this model and you have the main support which is not directly contacting with your model material. But which one is going to contact with model material? That is called a Sierra or a needle kind of a support, where it is direct contact with the model material. That which we need to much worrying about this. Why? Because how do you get detached this support once you complete this build, and we need to remove this support. So if it is a polymer, then you have either a breakaway or a solvent kind of solutions which you can even dissolve it, these supports. Or if it is a metal based system, you have this is also metal and this is also metal and made out of the same material. Then how do you get detached this? So for that reason, you may have several kinds of supports that you can use for that purpose. But still it should be one can understand much focus on this support structure. But support structure will have its own function to have be the anchor or role, or be the say a sort of overhang portions which we need to give a support. Or even it can be responsible for say heat transfer kind of a thing, say which we outrightly we never eliminate this support. Sometimes it is very much needed, but you try to minimize, and as well as it is possible, then you can try to do that. Then your design for additive manufacturing is going to talk about that. So your support structure sometimes, as I said, like it may not be every time as a curse, but sometimes it may be boon also. Say like some why? Because you didn't give any supports, you didn't provide any supports here, you may get some peeling action like this. But if you have given some support here, then you may get better the product here like this, without peeling or without say this kind of a defect. You can get it through the support. But like say, then you can have a more thought process on this, like how you are going to generate this support. But you may wonder why I'm saying this, but your software may automatically support. Yes, but it may automatically give some support, but what kind of a criteria it has been adopted, or whether it will vary from one geometry to other geometry, and if you vary the orientation. So all these things which we need to thoroughly analyzed, thoroughly retrospect. So the effects of this support structure versus your orientation versus your surface finish versus your build time versus your mechanical properties, all that things, right? And which we need to slice the model. Of course, the next one is once you fix the orientation, and once you have specified the say all sorts of this which we have discussed previously, and then you have specified the layer thickness, how much layer thickness, maybe 100 microns or 200 microns. So then you adopt that layer thickness, and you slice the model and generate the codes or generate the cross-sectional data, and then further you generate the tool paths the corresponding to that contours that it has been generated, right? So then how do you do that, and say this is the model and that it has been sliced during the slicing say operation, which you can do that. And if you see the mathematics involved behind this slicing, it is a simple understanding. So first of all, how do you get how do you find the total number of slices? So of course, the total number of slices can be a simple thing, like you have the z maximum minus z minimum of the part which you have fixed in a particular orientation by the number of, by the layer thickness. So then it will give you the how many number of layers that it has been required to fabricate that much height of your part. So that will dictate your number of layers, and that number of layers, then once you got the number of layers, these many number of layers, it is getting fabricated fine. So then how do you get your slice points? Like say you need to get generate a contour, right? So we need to generate a contour. For generating the contour, so then we need to get the slice points at the intersection of your cutting plane with the model STL file, that is a the triangle facet. So then you have a simple equation here to get your say slice point, the intersection point of your cutting plane with the model, and at that particular Z position, at that layer 1 or layer 2 or onto the platform, that is a 0th layer from the last layer. So you can make use of this simple geometrical equation, like where this is what I'm talking about. See, you have the model and you have the slicing plane, and it starts from the Z0 to Z maximum with an increment of layer thickness, maybe 100 microns or 200 microns or whatever it is. So then you will be getting an intersection point here with the previous equation, the simple equation, which you could be able to get an intersection point of the plane with the straight line or the side of the triangle, because it's a STL file. So you can get that say contour intersection points, and you have the two possible options. Either you join clockwise or either you join in anti-clockwise. Maybe you have a particular notation for that. Maybe that belongs to that facet, or that triangle belongs to an external feature of your product or internal feature of your product. So then that will dictate your the sense of joining of that. So you have the outer contour has been say traced, and we need to fill it up with your laser scan paths or your tool paths, basically, which we need to do that, right? And before that, even we need to identify certain peak features. What do you mean by a peak feature? So the peak feature is one, sometimes you may be say escape some of the features. Say for example, I have the layer thickness as say 200 microns, but my feature is the smallest feature here is say some 100 microns or 70 microns, for example, and you may get missed that a feature with this say 100 micron or 200 micron layer thickness, which it may be you may omit some of the features which is of lesser size, lesser than your layer thickness. So then we need to take some sort of care or some sort of analysis that how we can compensate this sort of thing by giving or by reducing the layer thickness or by adapting a sort of mechanism here without say omitting that feature. Then that is also job of your design for additive manufacturing guy, which we need to take care about these features. And once you got identified the peak features, and once you got the contours, or then how your contour data has been organized means, so you take at a particular slice or particular cross section where you may find say for example one of the um, uh, part is having this kind of a cross section, and you may have a hierarchical relation. Why? Because one feature may consist of several generations, may means parent child relation. So in that case, which we need to organize that data, internal external contours, identifying them and putting it in a hierarchical manner, say of course, that can be done by your software, but how it is doing, then can it be further improved? Can it be so done in most effective way? And once you have done that, so your code is ready. Say you have set everything, and you have fixed the layer thickness, and you have given the supports, and you have fixed the orientation, and you have sliced the model, and you have generated the contours, and you generated that code, cross-sectional code, and it will be sent to the machine, right? So that maybe typically it may be dot CLI or dot SLI, or it may be some other file format. It's a proprietary format. Normally, you don't have a standard format as of now, or till date. You don't have such a kind of a thing. Each one may be a proprietary code format which we should interface to the machine. So you take a typical CLI, that's a common layer interface format. So it consists of the entire the product data, like which it starts with, say you have the contour data organization, how many number of layers that the model is having, and the contour data of the first layer, you have some 10 layers or 100 layers. So the first layer, again, what is the layer index number, and what is the Z coordinate at that particular layer. So, and then how many number of contours that particular, say, layer is having. And you start with first contour, and you have the contour index number, and whether that is contour is a closed one or open one, and whether it is an internal contour or external contour, which we discussed previously, and it's a father contour or a child contour. If you tell that, then what sort of that one, and the number of contour points that is having that particular contour. Say how many contour points. Say I have some 20 contour points, which it will join and generate one contour, right? So and all that coordinates. So you have that the number of contour points, first contour point, the coordinates of that, x coordinate, y coordinate, and z coordinate of that, and like that you have all that the first contour, and you have the second contour information, and it may have some 10 number of contours at that particular layer, first layer. So you have all that information, and similarly for second layer, third layer, and you have 100 layers, all the 100 layers, this code or this common layer interface data will be basically, it's a polyline data, right? So it's a cross-sectional data, the coordinates that, and the organization of the each and every feature one upon other, then it has been set in that way, and it will be sent to the machine, right? So this is a typical and once you send that data, and you can have the provision that you can vary your tool path. So then you may use the contour first, how your layers will be built. If it is a laser driven system, laser will scan the outer contour first, and it is something like how an artist will sketch these sketches, right? Say he will do outer first, and then he will use a back and forth stroking of your thing, and similar way your laser or your deposition will be done. So it may be horizontal vertical combination or inclined, some raster angle or some contour raster combination. You can have a different tool path strategies, and that will dictate your scan time, that will dictate your build time, that will dictate your cost, and that will dictate your mechanical properties, and that will dictate your quality and other aspects, right? Say you can have a better control over a tool path and better selection. So which you have a lot of freedom here, but that freedom will be used in a more optimal way, right? So then how do you make use of that? The tool path generation could be done in such a way that you can get your design for additive manufacturing is say this is directly relating your geometry or your design, right? So some of them may not be directly affecting your outcome or your design. So, but here it is directly affecting your design. So if you redesign it, so then which we need to say consider all that stuff, right? So just like that, you cannot redesign. You should not redesign, or like how you are going to get the maximum benefits out of this. So that is the thing where we need to work on. So and sometimes you may come across some mesh repair, which oftenly we do. Say as we know that if you give garbage in, again you will get a garbage out. So if you are not giving a watertight model to your AM system or to your software, so what it is going to do, it will generate an error file or error model, or it may create a sort of build failure, or it may create say a faulty model, or it may fabricate. So which sometimes we need to do a repair, mesh repair or STL file repair or whatever, AMF or 3MF or any format that we need to going to send to the AM machine or AM software, interfacing software, which before that we need to check whether it is free from all the errors or not. Sometimes we need to repair that mesh, or we need to say add editing of your STL file. Why you want to edit the STL file means like you might have received one of the CAD designs from your customer. You are running a service bureau. Then you want to give a label onto the part, or you want to take some measurements. You cannot do that on any STL file. I don't know like how many people are tested this. At the moment you saved as STL file, it becomes static. You cannot it is not in editable format. You cannot edit, but you cannot very well edit a native format like .prt or .part or whatever the package oriented native file, the file extension. But the STL file, you never, it won't allow you to do all this. But you oftenly need some take some measurements on your STL file, or you oftenly wants to give some labeling, or you wants to give some painting, or you want to make it hollowing it out. Just now we have discussed that is the masses, the large masses is going to consume a lot of material, lot of time, but which we need to coming out some sort of hollowing it out, or porous structure sometimes intentionally, or sometimes some honeycomb structures, or sometimes your topology optimization, right? We have all these capabilities of additive manufacturing, which if you are not using this at the maximum extent, but you are not a good user of additive manufacturing technology, undoubtedly. So then how do you make use of all these capabilities? Like so that should start from the design, right? So you are not saying that I'm going to, okay, we'll see at the end, that is during build or after build. No, that should come in the design itself, right? Say that's the thing where we need to focus much on the design aspects of additive manufacturing, why it is so important, or gaining a lot of interest for the recent times. So anyway, so the cutting, sometimes we need to say cut it, or sometimes we need to Boolean operations will be performed. Sometimes we need to smoothen it. But unfortunately, your CAD, neither your CAD package nor your AM um, package interfacing software doesn't have this capability. So then, which we may adapt the third intermediate package or intermediate software or system to do this job. But once your STL is replaced with an AMF or a 3MF files, but it is not happening so far. But you can anticipate maybe in future or near future. Then it is quite handy, but still so far it's not happening. But you sometimes we need to do some sort of repairing of your STL files for better visualization, or flipping of normals, or flipping of triangles, or stitching of your triangular mesh. One of the triangles got missed and we need to automatically stitch them, or sometimes we need to do a triangulation automatically, or sometimes we need to do a manual repair. Something is wrong in your design, reasons or many, maybe while um, transferring this data, converting the data from one form to other form, or um, maybe several reasons. But this might have come from say point cloud data, maybe through the scanning um, a domain. But oftenly you may require these sort of repairs. So then how do you get do this kind of repairs, whether it should be done through manual or automatic repairs? So of course, which we are talking about a support structure, the support structure which we need to vary the support structure style as the feature that requires supports, like say which we need to have a huge area, a large area is needed to give in support, then you go with the block support. But you have very narrow area which requires support and go with the line support, or you have a sort of very small feature that requires support, you go with some point support, or you have some overhang feature, it requires then supports, then go with the gadget support, or you have some circular features, then we go with the web supports, like that, where you have to vary the different supports as for the feature. That is a one way of doing it, or you can redesign the feature, that may be the another way. But if you doesn't want to redesign the feature, but at least you manipulate these supports, right? Say and then you have a slicer softwares like to generate this G code or generate the CLI or SLI files right from the STL or OBJ or X3D or 3MF or AMF or any sort of thing, and which you are going to generate a slice data or a G code data, and it will be sent to the printer, and you have the G code here, and you have the slicer which creates a topology based on your geometry, and it will also say add the percentage of infill material inside your the contour, and then you have the support structure if the geometry is say difficult to print it, and then so on and so forth, which we need to, your slicer has to do that. And you have a lot of open source slicer softwares available, say Cura, one among, and then this is mainly meant for a sort of extrusion based um, systems, which it can you can download as a free of cost, and you can make use of these kind of softwares, and you can find some of the STL file repair softwares like which you, some of them may be the open source um, nature also, like Mesh Mixer, um, NetFab, or maybe if you are looking some proprietary software may like Magix, and you may have other softwares also to fix your STL file problems. And further, if you are looking for the slicer software like Cura, Simplify 3D, and other open source softwares can also be used for the slicing purposes, slicer engine for in order to generate the slices. And then the unique capability, as we are discussing, the topology optimized structures, right? So through additively manufactured practice, and then bionic designs, which has been nature inspired or biology inspired designs, then it's quite um, common or quite encouraging, fabricated through additive manufacturing rather than a conventional manufacturing practice. So you may come across several tools nowadays to have a topology optimized structures or the bionic designs or a sort of generative designs, right? Say if you see this scenario, you have a parametric design followed by generative designs. Now you have a topology optimized structures or lattice structures, biomimicry or bionic designs, where you have then nature inspired or lattice structured based designs, or even topology optimized the material reduction, weight reduction applications, or part consolidation applications, where you have a huge scope in the manufacturing process. So topology optimized structures or lattice structures are the bionic designs. How do you get fabricated, right? So that's the thing where am is shining, right, under all these say applications like um, and you may find certain topology optimized softwares like Altair OptiStract, and you may have other softwares also to perform a topology optimization. So you can create your design space and you apply the constraints and you scoop out all the material. So without performing or contributing any functionality in your product, and without compromising the functionality, rather than with the improved functionality, right? And even improved, say, utilization of the space, more compacted area, the less volume it's going to consume rather than the traditional design approach, right? So you can keep on talking about these aspects, like which you can uh, talk about, right? Say, and say your build simulation softwares for AM, that is quite obvious. Why? Because as we know that especially for metal systems it is quite expensive. Then how do you you don't have a luxury to waste these powders or running hours together onto the machines, but we don't have a luxury, and if something goes wrong, just you need to have some sort of simulation, some sort of multi-physics oriented modeling, so to predict some distortion in your while fabrication. Say we need to predict some sort of say, definitely you have a lot of residual stresses inside, within the layer or within at the interstitials. So then how do you say tackle that, and which you have some sort of a simulation system which it can even compensate it, getting compensated this distortion or the shrinkage sort of defects which you can normally you come across. Why? Because you are operating at high temperature gradients, right? So that is the biggest issue or the biggest challenge in any. You may be operating all the way to 1200 degrees C or 1500 degrees C, or even that is going at the fraction of seconds, or maybe within the milliseconds or within the um, seconds which it is going. That like where we need to take much care. Otherwise, you maybe end up with a sort of defects, right? And which also it also your simulation studies will also suggest some sort of distortion compensations, or so it will also suggest the best support structure generation, and it also minimize the risk of printer damage, to recoater damage, to minimize the number of build tryouts, or which also it will predict the post processing effects like heat treatment or hipping or support removal and so on and so forth. So we have orientation is going to play a major role, which we have been talking about. and support configuration, and which would have a lot of say distortion kind of a things, problems due to residual stresses and plastic strains, all that things. Maybe it depends again type of material, whether it's a polymer or metal, or within the metal you have several metal material, the metal alloys. So all the way which we need to even say take care about all these things which we should consider all these things, and you simulate it, and better you can save a lot of time, a lot of money, or you can minimize a lot of defects um, uh, in this course, right? So even you can have a simulation softwares like from ANSYS, Additive Print, 3D Systems, 3D Expert, and you have other say from Hexagon, Simufact, Autodesk, Netfab, some extent it will do, and Sim Center from Siemens. And you have a majority of the systems from work for the metal AM system, that to a powder bed fusion system. But still, you have potential that should be tapped in this direction. So then how do you get selected your AM technology by the material? Why? Because not all materials can be processed in a single AM technology, but we need to select a particular uh, machine or particular technology to have that. So you may have a different material options, right, from the polymers to metals to ceramics to composites to functional materials to bionic materials to food and other organic materials, natural materials. You have a huge potential, and then you may come with different forms of the materials, right, from the powder to filament, wire, rod, or laminates or liquid. So but anyway, I don't want to discuss on these various EM processes, but you have some certain ISO ASTM standards to standardize these processes. And of course the material, like you can have polymer, metal, others. So you need to either it is a thermoset plastic or a thermoplastic, or if it is a epoxy resin or it is a acrylate, then you have to choose a particular, or you have to select a particular technology, and you have the metals and others, then which we need to come out with a sort of selection among these technologies. And this selection may be based on the application which you may have, and the feedstock may be of liquid, powder, solid, as we discussed, and you have a 7 processes, but it may leads to the feedstock before the process. You can find some cross linkaging here and there. You have a huge developments are happening under each and every process. So to have multiple materials, or multi-structured components or functionally graded materials, so it is now quite possible. Maybe different principles across polymerization, inkjet, automation, atomizing your powder or atomizing your liquids can also be, or melting, solidification, joining. You may have a different principles and different ASTM or ISO classified systems. And basically you have, say, functionality is your application, functional application, whether form fit applications you are looking for, and what is the tolerance that you are looking at, the low level tolerance, medium level, high level, and we need to choose an appropriate machine. You may not be getting these on a single machine, or if not, you need to do some post processing. Otherwise, if you have some choice of options to choose, and then you can go with these options, maybe high strength, maybe less than 30 MPa or greater than 85 MPa, then use and choose an appropriate technology. And special purposes, chemically resistive, heat flammable, or biocompatible, you need to choose an appropriate and flexible flexible material for some sort of applications, highly elongated or a soft rubber kind of a thing, or even for visualization application, smooth surfaces you need, or transparent nature you need, and then whether the support marks are accepted or not. no means you can go with certain uh, selection, or S means you can choose some other technology. And then textures, you need wood fill textures, metal fill, rubber like, or you need to print some colored models for in polymer or sand. Then you can choose to process. Why? Because say for example you have a support wall like this. This support wall thickness may be varying from one process to other process. You have a certain constraints of each and every process. So some of the process like FDM, we should not go less than 0.8 mm once you come across this sort of feature. It may go up to zero point 0.5 in case of a VAT based system, or it may be zero point 0.7 in case of a powder based system like say SLS. On it may be unsupported wall for other feature like this. It may be zero point 0.8 for extrusion based system like FDM, and it may be 1 mm, and it doesn't require. Why? Because powder will act as support. So it doesn't require a sort of this thing here. And then support and overhangs, the angle may be varying from process to process. So it may be 45, or supports are always required for SLA. You cannot eliminate powder bed, it doesn't require any supports. Like so, which we can see that each feature may be process dependent. Like then, how do you fix, or how do you say your design for additive manufacturing is all about? So we need to thoroughly know about these constraints of each and every process, each and every feature on which machine, and accordingly we need to redesign sometimes your product designs, right? And then you have some embossing or engraving details, and you have a certain values which we need to follow. That values, that numbers will be varying from process to process. And you have some horizontal bridge kind of a feature, then we should not go less than 10 mm if you are processing on extrusion based system. But it doesn't matter. Why? Because you have a vat of liquid here as a surrounding, but you have powder here. That's what it doesn't. But FDM, it is as for the demand it is supplying. So like DED is also same thing for metal printing. But see, like, which we need to understand each and every process and each and every constraint in each and every feature, right? So then what is the minimum hole diameter that you go with each and every process, right? So it may be 2 mm, it may be 0.5 mm, 1.5. So it will vary from process to process. You cannot generalize um, these features, right? This is about the three processes, and you have another three processes, the same features, which you can see the different values. So then that's what where we need to have these design rules thoroughly. You must understand. Then only you will become a good design for additive manufacturing user, right? And you may have some connecting or moving parts, so which it have some mating parts. So then what could be the tolerance that you're going to, or we need to say give some space, right? So zero point 0.5, zero point 0.5, maybe zero point 0.3. And you have escape holes. The escape holes you need not for FDM, so because as per the demand it is depositing it. But a liquid surrounded or a powder surrounded, which we need to evacuate that powder, otherwise it will be there inside your model, right? So it will add some weight to, or you are not you doesn't want to leave that inside. Then we need to provide some escape holes. So then what is the minimum size of the escape hole? So it will vary from process to process. And you have a minimum feature of this sort, maybe 2 mm for FDM, 1.2 and zero point 0.8. Why these different values? So why? Because FDM is a mechanical based system, like in a nozzle, and you have the thermal energy. But whereas a stereolithography or a VAT based system or a powder based system, you have a laser and the optics controllers, optics driven system. So where it may be more precise, right? So you can get that's the thing where we need to know about these constraints, and you have a pin diameter maybe 3 mm, 0.5, 0.8, and tolerance maybe plus or minus 0.5, 0.5, 0.3, or whatever. Say which we need to say look all this. Then only you will become a good user of additive manufacturing technology. Otherwise, not. So simply, it is not just migrating from the say conventional subtractive or formative process to AM. No, altogether you have to have a different mindset and different thinking process. Your design thinking is totally different, right? So this is what quite long time, maybe 1.5 hour, 1 hour 40 minutes you have been talking about these things, right? And even the same features, if you want to say produce through other processes, like which you can see all these values. And further, for anybody is interested, you can refer some data handbooks available on this, which you can refer certain websites like a 3D hubs, or you can refer other resources where you can get all these information, or even you can go visit the Purdue uh, University's C Lab, where they have come out with a sort of design for additive manufacturing as a workflow. So just you can say supply your design, and say they have made weightage, or they have given some matrices for each and every area, like they have divided the the the, the design into the complexity wise, the functionality wise, material removal wise, unsupported features wise, thin feature, stress concentration, tolerance, geometric exactness. So they have come out with a sort of, just you evaluate your design, say just you evaluate your design and get the score of each and every category. And if your overall score is say 8 to 15, so it doesn't require any changes at all. But your score is around 16 to 23, so there will be a moderate say likelihood of the success of your printing. Then if your score is a bit 25 to 32, so we need to consider for the redesigning of the product. This is not as for the additive philosophy. Probably it may be the other philosophy, but once you want to use it, then definitely it may, you may consider for the redesigning. But your score is quite big figure like 33 to 40, then definitely we are not ignored for the need for the redesign, say, which we need to say come out with this sort of evaluation of your thing, and then get it, and accordingly we need to do that, right? Say then before concluding this session, like say what is the scenario of your the standards, why you are talking about the standards, means say it is very tough every time saying that say so more complex, the more freedom, so it may leads to a lot of complexity, or a lot of what you call say your additive manufacturing is meant for a lot of customization, personalization, right? And it's much attractive for complex geometries, and part consolidation, and minimizing the weights. You have several design freedoms in case of additive manufacturing, but that may sometimes restrict um, the sort of standardization process. But though the standardization come a bit later, why? Because AM journey has started 32-year back, but your ASTM ISO for F42 committee, and forming for a sort of uh, developing the standards for AM, that has been initiated 20-year ago, means you have 10-year gap. For the past 20 years also, hardly you can find around 35 to 50 ASTM or ISO or combined standards, or in total as published is around 35 to 50, but it's less number. But still it should be further say expedite this process. So it is very much needed. Why? Because still the industrial adoption of this technology is not that much great. The reasons, or once you have certain standards, then people will blindly say follow that, and people will have a lot of confidence or adaptation, right? So anyway, that is a big subject to be discussed and say debated. But anyway, so you have ISO STM terminology standards, or the design related standards, or fabrication related standards, or feedstock related standards. So you can get it from the various sources, the ASTM website, or ISO, or even get some other places like say, but which you can find a lot of scope to further add these standards in all these say 4 directions, or in any other direction which we need to get these standards. And let me summarize what I have done for the 1 hour 45 minutes. So we have started with the importance of AM design and various AM tools and the softwares. And initially we discussed the conventional approach, or the part replacement versus AM adoption versus design for AM, that is DFAM, um, uh, the design philosophy of additive manufacturing, the importance of design for additive manufacturing, and the process plan, of course, and the importance of part orientation, the selection or the fixation of part orientation, or the support structure generation, say, which otherwise it will have a lot of effect on your post processing time and the cost, the total cost, it's going to badly affected by your support structure and part orientation. Mesh repairs, why when you want to do, and how do you do this mesh repair, and slicing, tool path generation, so that we thoroughly discussed under this process plan of AM. And we have a little bit touched about the topology optimization and the bionic designs, and the need for additive manufacturing, and in particular DFAM, design for additive manufacturing, and selection of AM technologies, and the design rules for additive manufacturing. So that's what we have discussed. Yeah, and coming to the facilities which we have at NIT Warangal, we have a metal additive manufacturing system of 3D systems. Say it is a metal-based system which you can process aluminum, which can process say titanium, nickel, stainless steel, and we have a Stratasys make polymer printers, Dimension series machine from Stratasys, and Mojo series from Stratasys, polymer printing, and desktop printers like Ultimaker 2 Plus, and couple of scanners, AnyScan and SenseScan 3D scanners, and muffle furnace for the post processing, or the furnace treatment for metal 3D printed parts, and short pinning and other accessories to post process your metal 3D printed parts. And we have AM softwares. So we have a Mimic software for processing of medical image data, like DICOM images, and say Magic software for repair of STL file, and then generating some tool designs for AM, and then thematic software for designing the medical implants, and we have Catalyst software for say pre-processing of products for Stratasys make machines, and 3D Expert for metal powder-based system, powder bed system metal printers for even modeling of supports, simulation, multi-physics modeling. So things will be done under the 3D Expert software. So these are some of the facilities we have at NIT Warangal. And yeah, if you are having any questions, I'm very happy to answer those questions, then yeah, I'm concluding my talk here. It is over to you, the organizers. So to getting connected with the participants to have certain clarifications or queries or the suggestions.
Yes, sir. Okay, participants, any questions? Please unmute yourself and ask the questions. Participants, please ask the questions. If any doubts, any clarification needed, any help required. Okay, there is one question, sir, in the chat box from Muhammad
Okay.
Afzal, instructor, University Polytechnic. How can we differentiate between RP and AM?
Mm, yeah, RP, rapid prototyping, it was the initial name of this technology. So it got evolved. The 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 scope of applicability of this technology. Initially, it was only to fabricate the prototypes. So means the maturity or the level of um, properties that you're going to get, maybe for prototyping purpose people used to use this technology. That is at the very beginning, but still now also you have the applications, prototyping applications and product design applications. But now it has been dominated by the direct metal or direct end usage parts. So that is quite maturity in the recent times of this technology. It has been, say, promoted from the prototyping or the designer tool to the manufacturer tool. That's what it has been, enhanced the scope of these parts. It has been printed. Yeah. So yeah, it's a level of maturity of this technology. So if you see in that, say, your application of these parts that you have fabricated through this technology. Nowadays, these are interchangeable. These names are additive manufacturing, rapid prototyping, 3D printing. So, which we can see that the capability or the applicability of these parts may be restricted to prototyping. Maybe that was the initial application and the initial name of this technology. But now it is been additive manufacturing. That is a manufacturer's tool rather than a designer's tool. Predominantly, previously it was, right. Yeah.
Another question, sir, from Deepak Kumar.
Mhm.
The question is, can we will able to obtain a desired strength in metal additive manufacturing process?
Yeah, of course you can achieve the desired strength. Yeah, we can put it in this way, like if you try to, that depends again, like say you are as we discussed, some extent your design for additive manufacturing is going to play a vital role to bridge this gap between your desired strength that you achieve through conventionally made, conventionally machined part, or forged parts or casted parts. I think your question may be in that direction. So I can put it in this way. Say, if you are making use of, say, forging process, you try to compare the desired strength or the your mechanical strength. One route is through, say, forging, and you have the casted one, and you have the additively manufactured route. Say, definitely, it is undoubtedly, it is on par with casting, and it may be a, a bit inferior than forging, but definitely it will you can fit it this in between casting and forging. So, and sometimes it may be better also, sometimes it may be better also. um, yeah. So you have a sort of flexibility or freedom here, but this should be further post-processed. I'm not talking about head-to-head comparison of as-built components, but I'm talking about if you add some post-processing methods also, like heat treatment or like your hipping or like your short pinning, but definitely as-built, if you compare, it's not comparable with the machined components. Why? Because we have been discussing anisotropy, or we have been discussing other say defects or the sort of things which you are going to inevitable in additive manufacturing. But we can bridge that gap maybe through good design for additive manufacturing usage, or with post-processing methods, which you can, yeah, definitely you can get it done, right? I hope I answered your question, Deepak Kumar.
Okay. There is one more question from Dr. Rupendra Nehte. The question is, any Indian standards existing for AM?
No, 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 no. No, actually, still, um, yeah, as far as my knowledge goes, there are no Indian standards, but hardly in ISO or AM together, the ISTM together, um, they are working, and even maybe you may hardly find other standards also, but ASTM, ISO, you can find reasonably around 35 to 50 has been published, and another 35 to 50 under development. But there are no Indian standards as far as my knowledge goes.
Okay. Then one more question from Natraj Kumar Singaraju. The question is, which is the most user-friendly mesh editing software while design?
Mm. No, I'm not expert in this area, but like say, which say you can even use for mesh editing. Uh, Maybe you can try with no, whether you are looking for the proprietary softwares or the user the open source softwares. You open source software, some extent you can do a sort of mesh mixture, um, mesh lab, or proprietary softwares, um, maybe with the perspective of EAM, maybe you can Magix, maybe some extent, or Rhinoceros, maybe you can try. So no, uh, I'm not say a representative of any of these companies, but you can try these softwares.
Yeah, one more on from the Vikrant Gokhale. Any FEA has been done on 3D products?
FEA. No, actually, his question may be like no. FEA is a tool to do a finite element modeling. Like, so modeling